So we will start with very simple example. Uh, okay. So assume that is we have an insulated duct. This means there's no heat in. Okay. Remember the closed control volume or Reynolds transport theory. So there's no heat transfer. It is mean adiabatic, and due to uh, the friction by anyhow. We assume there is a friction here, so due to the friction is the pressure going to change, okay? Or assume that is there is a pressure here, etc. Okay, so we know B1, V1, and we know T1 has been given. It's not the definition; it is an actual point. And the diameter. From the diameter, we can calculate the area. From the area, and from it is air, so gamma r T1, and so we can calculate the speed of sound here. Then we can calculate the Mach number because we know the velocity 1. So Mach number equal 0.3. Because it is 0.3, uh, we can say it is likely will be compressible. Under 0.3, it is not compressible. So we need to calculate the stagnation. First, when we do any work, we need to find what is the stagnation, pressure, temperature for the line. Why? Because he said to us that the stick here at the exit, Mach number equal 1. At the exit, Mach number equal 1. Okay, so we need to calculate the stagnation pressure. Stagnation pressure is pressure number 1 plus. We know Mach number here it is equal 0.3 square, etc. So the stagnation pressure is this one. We know stagnation pressure at 1 and 2 is equal and constant. By the way, in another way, we cannot use this one. We can use the other one, which is B stagnation is equal B1 plus half rho the density multiplied by V1 square. Rho is equal to half B over RT 111. So you will get exactly the same answer here for the stagnation. Okay. Uh, Now, based on his told us there is a shock here, which is mean B equal B star, and we know that is B star over B naught, which is here equal this number for air. So we can calculate B2, which is equal B star. So B2 equal B star. Okay. So which is equal to stagnation pressure we just calculated multiplied by gammas and etc. So B2 equal this number. Same concept, we can calculate T stagnation. Same from this formula. T stagnation, okay. T stagnation is constant everywhere. So T stagnation at 1 equal T stagnation at 2, and we know that this temperature at 2 is T star because it is Mach number 1. So we can use the same equation here, T stagnation multiply. Based on this, we can take temperature 2. If I have temperature 2 and pressure 2, I can calculate the density 2 B2 over T2, and this is the density in 2, and the same, and this is the density for 1. If I have the density for 2 or density for 1, just keep it with you. But also I can know what is the mass flow rate. Mass flow rate anywhere it is V1 area 1 or V2 area 2 area 2 to be constant the same. So it is 10.39 kilo gram per second. So if I want to calculate what is the exit velocity is very simple. It is m dot equal or whatever it is, m dot equal O2 A2 V2, or you can calculate it based on Mach because I know Mach number equal 1. From Mach number equal 1 I can calculate C speed of sound. It is not constant based on T1 T2, so C2 equal gamma R T2. So I can calculate C2 equal to velocity 2, or I can calculate it based on mass flow rate. Mass flow rate is rho 1 V1 A1, so I can calculate it with the same both will giving you the same result. Now, if I want all of this, I want to calculate what is the force when the air is pushed like this. So there is a reaction force like this. So what is the force? We agreed that is the force, if we remember, in water, like here, an example, if I have water jet and I have Vn, V out, so I have force, same concept. Control volume, apply the control volume. Control volume saying that is B1, area 1, minus B2, area 2, plus the force, equal force plus the force equal to m dot V2 minus V1. What has happened? It is the same philosophy. So, 1 second, just to be in very simple manner. I have pressure here, I have pressure here. So pressure here and the pressure here, velocity here, velocity here. So equal the force. If we divide it by area, divided this one by area and OG, divided by area and OG, divided by area and OG. So this one will be pressure by the way, and OG will become head. This become head, head, head. So at the end it will be heads. Okay, same control volume. So it is delta B multiplied by area minus velocity is the kinetic. So the pressure energy, delta pressure energy minus delta kinetic energy, it is equal the resultant force. Of course it's not energy, but if I set as an approximation, so apply, you will get Newton. Of course it will be minus because it is in opposite direction from x. This is very simple, straightforward. Okay, the next example, it will be become complicated each example and afterward. Assuming that we have a reservoir and the reservoir having an outlet and the outlet taking a shape of converging, diverging nozzle, and we know that the outlet is going to supply or discharge the air in the air, sorry, and this is air, which is giving us that they give us that area at the exit and area at the throat, and they give us also the back pressure, also giving us stage, or sorry, the stagnation pressure, which is the pressure of the reservoir, and stagnation temperature, and assume that the temperature is constant here, which is not going to change while the pressure is going less. It is an assumption. Okay. Now we need. Okay. Now, while they already write all of this, so maybe they will. The question is, okay, what is the velocity at the exit, and what is the discharge flow rate? Okay, in this condition, like we need to know, okay, what is the discharge flow rate and the velocity and etc. Okay, first of all, we need to calculate the definition of B star. In case if there is here in the soil Mach number equal 1, we need to check what is B star should be here. Okay, it is very simple. We know B stagnation is this number, right? Gamma is 1.4, so blah blah blah. Then we can calculate B star. Okay, while we know that is back pressure is less than B star, which is should be, so the flow rate will go and it will reach to B star. So it will be shocked at nozzle. First. Second, and the pressure at the throat will be B star. It cannot go less. Based on this, we can calculate T star. same, we know stagnation temperature. From B star, T star, we can calculate C at the throat, or the speed of sound at the throat. It is T throat, which is T star, multiply all of this number, and we know it is Mach number 1, so the velocity at the throat it is this number. From the throat condition, we know, or they told us, the area of the throat is this one, and I know the pressure at the throat, which is P star. T star I know it, which is temperature at the throat. So V throat I know it, which is C. A throat I know it, so I can calculate density, and I calculate the mass flow rate, and the mass flow rate is constant. But because also I know it is here, so Mach number equal 1, so here the area is A star. It is a fact. Okay, so area exit divided by A star as an area, it is area exit divided by area throat. What is it is 3.5. Simple, 3.5. The area what we have divided the area the given. Based on this, we can calculate from the table or by trial and error the exit velocity, because I used area exit. So area exit, I can calculate the Mach at the area exit either by trial and error for this equation or from the table. Okay, what is 3.5? Go to the thermodynamic table. We just here, yes, it is 3.5, 3.5, 3.5. It is almost this one. So, sorry. 3.5, it is almost this one. So Mach number should be equal to 2.8 or 2.8 or the other uh, Mach number, which is between these two, maybe 0.25 or something. Or we can use the graph, area over area, it is 3.5, which is we don't have it. It will go like this. It is 2.8, which is the graph is not fully, but use the table. Okay, okay, when you go check Mach number 2.8 or 0.17. 2.5. Okay, okay. So we know Mach number at the exit. Okay. While we know Mach number at the exit, we need to check this. Yes, calculation showing us Mach number at the exit, it is 2.8, which is supersonic. But we know if there is a normal shock happen, this will not be valid. How to check normal shock? We need to check the stagnation pressure. Is it less than the exit pressure theoretically or no? So we need to write, assuming there's no normal shock now, and we can calculate B exit. B stagnation of B exit equals this one, so we can calculate B exit. So this is the B exit pressure. Now B exit pressure, and because the pressure back pressure is a stagnation pressure, because the air atmosphere is not moving, and because of B exit is bigger than the stagnation pressure, so our assumption is correct. Okay, so yes, Mach number is up. Okay, if I need to know also what is the remaining parameters like the velocity, okay, I know the pressure, I know Mach number, and I need to calculate the velocity. Calculate the velocity, you need to turn back to C. C equal, because you have Mach number, you need to calculate C. To calculate C, you need T exit. Okay, so let's calculate the exit. T stagnation over T exit equation. We know Mach number equal like this, we know like this, so T exit is like this. So C exit is like this. So V exit is C exit multiplied by Mach number of exit, which is this velocity. Another assumption, if the pressure in the tank reduced to 5 multiplied 10 of power 6 Pascal, we need to repeat the same. Yes, it is B star is like this, bigger, so it is shocked at nozzle. Then we calculate C at throat, same mass flow rate, same, it's okay. Then Mach, to write calculation Mach at exit. Of course, it will become the same number. Huh? Why become the same number? Because horsepower equation or formula, it is a definition of A over A. That's it, nothing else. A over A and nothing else except Mach. So yes, we need to get, it must be the same Mach number. But now we need to check B stagnation is like this, exit pressure is like this. Exit pressure is 1.84 multiplied by 10 of power 5. Stagnation pressure is just 10.5, 10 power 5, which is still we are higher, B exit higher than B stagnation. So yes, there will be no normal shock. So yes, it will be everything is okay, same procedure. Our assumption is correct, so calculate C, then calculate the velocity. The velocity will become 606. So last question is, if there is a shock, normal shock, happen at the exit itself, which is mean B exit should be equal to stagnation pressure at the outside, which is B exit should equal this one. What is the stagnation pressure? Normally, if I know the B exit, because the question is what is the reservoir pressure will be. So stagnation pressure equal B exit, which is equal B back pressure, which I know it. It's this one. So it is clear. So this is stagnation pressure of the tank, and this is B exit, which is 10 bar 5, which is stagnation pressure at the air outside. To calculate the numbers, okay? Of course, there is a condition here as A over A star is not changed, so Mach number at exit is the same. It is 2.8. So put 2.8 here, B exit, B naught become B naught. So when the tank pressure becomes this number, normal shock will happen at the exit. If you know, if you want to calculate also the temperature at the exit, how much it will be, T stagnation multiply extra, so you'll find this one. From this one you have T exit, okay, because T stagnation never change. So C exit equals this number, so the velocity will equal this number, and the mass flow rate will equal this number. And case no shock at the throat, which is mean there is no shock here, which is mean Mach number not equal 1. So it should be pressure here will be equal, just equal the back pressure here. Okay, so pressure at the throat, which is B star, just equal to B back. So B star should equal this number, so B naught equal this number. So if the reservoir pressure less or reach to this number, it normal shock will happen at exit. If it is reduced more and more till reach to this number, there is no sonic at the throat. And still there's two examples. Assuming a convergent divergent duct, and there is throat at the nozzle, and there is exit. From the experiment, we found that there is a shock at the exit. There is a normal shock at the exit. Those clash happen. Okay. And we know it is air. We know R. We know the area of the throat. We know the area of the exit. And the back pressure, it is the air atmospheric 10 power 5 Pascal. And the T stagnation, here reservoir, which is 300 Kelvin. Okay. Okay. So now we need to calculate, okay, based on this information, what is the pressure here, stagnation pressure or total pressure, which is means stagnation pressure. Based on, we know here there is a normal shock, so by any mean here's Mach number equal 1. So when I know that is Mach number equal 1, so B here is B star, which is as the thought, and B exit should be just equal to back pressure. B exit should be equal, because normal shock at the exit. Okay, so AE over E star, put from thermodynamic table or try and error, you will get Mach number at exit this number or this number. We're going to take this number because it's supersonic. Okay, so B naught over B exit. B exit we know it because it is the back pressure as there is normal shock. So we can calculate B stagnation or total pressure at the start if there is a reservoir here. Same concept also if I want to calculate the velocity, etc. Any information here. So T naught over T exit, I know T naught. So I can calculate T exit based on Mach number, I know it now, 1.8. So from T I can calculate C. From C I can calculate the velocity. C I know it, Mach number I know it, so I can calculate C. Also, based on this, mass flow rate is equal to V exit, O exit, V exit, area exit, which is B exit over R exit, 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 exit. All I know, which is equal the mass flow rate. Okay, now if I want to check the lowest back pressure, we need to check uh, so if I want to go and check what is the lowest back pressure that will create no choke at the nozzle, no choke or just making the choke, which is mean B thought equal BT, and just to have shock you need the back pressure will be just equal the B thought. So B stagnation should equal to 5.7 this is stagnation pressure, which is B star, which is equal to, so B back must be bigger than 3.04 multiplied by 10 power Pascal. The certain written, which is what is the lowest back pressure, which is mean outside, to make the flow subsonic. Again, if the back pressure here get high, it will create no shock here. If the back pressure get less and less, less and less, it will create here sonic speed. So what is the pressure when I'm reducing it to create sonic speed? Okay, of course if I reduce it more it will create supersonic. Okay, but I'm talking about sonic speed. So if the B thought just equal the back pressure, so it's just sonic, which is happening here. So B thought should equal just the back pressure. Okay, okay, return back. Okay, so because we know that is B star or B thought equal to the stagnation pressure, from where we get the stagnation pressure, it is from here in the reservoir multiplied by this one, so we'll get B thought. So back pressure just must be just bigger or equal to this number to be subsonic or just to be a sonic. Okay, and case of nozzle, case of full nozzle. Yeah, okay. No, this was the other one. So the back pressure should be just equal or bigger than this number. So if the back pressure reduce than this number, it will be sonic. Okay? Okay. Last example. Have conversion, diverging duct. T stagnation we know. B stagnation we know. Area exit we know. Area throat we know. And we provided a YouTube manometer or a YouTube, and this is a mercury, and we found what is the delta H, and this is the density of the mercury, and this is the height of the mercury. So it is delta B can be calculated very easily, like rho GH, rho of the mercury, H of the mercury, G equal delta P, so delta B with us, okay, between here and here. So B exit minus, or C, it is not connected to exit, it is to stagnation pressure. So B back pressure stagnation minus T throat, we know it. Okay, let's keep it in our mind. For without calculation, we know from this shape is B throat is bigger than B stagnation outside from this one, because there is a height here. If this one is up and this one low, so we know the pressure stagnation is higher than this one. But because this one is higher than this stagnation pressure or back pressure, 1000%, 1000%, there is a shock here, which is mean velocity equal sound speed. So B here is B star, and B stagnation, we know it, B star, we know it. So I know this one, I know this one, I know this one minus this one, so I know this one. Okay, so B star, it's okay. So the case, we know it based on the case of shock at the nozzle. This is B star, that is B back is flow is shocked at the nozzle. By the way, because we know that is area percentage, which is just I have doubt about it. 3.15 divided by 9 multiplied by, yes, it's 3.5. Okay, it is 3.5, correct. Because I know the Mach number equal 2.8 from the table or enter or try and error. So it is supersonic for sure, because we know here is sonic. Still, I don't know if there is normal shock or no, but still the assumption. Because delta B I know, rho GH, and I know that is back pressure equal B star minus delta B. So back pressure is this one. Then stop. If back pressure is equal this one, I need to calculate pressure at the exit and compare to the back pressure to know if there is normal shock or no. So my assumption is correct or no. Let's calculate the exit pressure. Theoretically, exit pressure is equal to stagnation pressure. I already have it. Multiply divided by this one, the same equation that we were using before. Stagnation pressure from, okay. Then this one. Compare these two together. So the exit pressure, and this is the back pressure. Back pressure is bigger than stagnation, bigger than exit pressure. Stagnation back pressure is bigger than exit pressure. So there is a normal shock going to be happen. There is a normal shock going to be happen. Cases no is case nozzle full give supersonic. B exit should be equal, should be bigger than this one. If in case I need it not to be no normal shock, by the way, so the exit Mach number is not 2.8, so it's not valid anymore. Okay, but based on this, we know there is will be a normal shock. But in case if I don't want to have a normal shock, okay, exit pressure should be bigger than the back pressure. Okay, back pressure, we know it. So based on back pressure, I know it. Delta B back pressure equal the this one is fixed because this is B star.
the pressure start at the nozzle, it is cannot be changed, and back pressure I know, stagnation I know, so I just need to know how much should be the reading of the YouTube. So in case of supersonic and shock at the exit, just shocked, normal shocked at the exit, so B exit should be back pressure. Put the equation, so delta B, the reading of the YouTube barometer. Then you can calculate H, so H should be 1.118 meter. And this is the last example. This is a new subject regarding boundary layer.